Hey, what's up, guys? This is Chung here again. So let's take a look at LeetCode 505, the maze number 2. I believe you guys must have already seen the maze number 1, right? So this one is pretty similar, but actually it's not that similar. The description is the same, but the output is different. So this time, basically, there's a ball in the maze, right? And and then the ball can go through the empty spaces by rolling into 4 directions, but it won't stop rolling until it hits a wall. Okay. And then when the ball stops, it could choose the next direction. Okay. Now you're given like this m times n maze and the starting position of a ball and a destination position. And then you need to return the shortest distance for the ball to stop at the destination, right? If the ball cannot stop at destination, return -1. So the distance is the number of empty spaces traveled by the ball from the start position. Okay, and you may assume the borders of the maze are all walls, right? So that's why. So here, for example, this one, right? The ball starts from here, and then the destination or the gate is this one, and the answer is 12. And why is that? Because so the ball roll to here first, right? And then from here it go down. From here it go to left, right? And then it go down again. Then it go to right, and then it go down, and then it go right. So this is the optimal path this ball can reach to the destination, right? And the total distance is what? We have 1, right? 1 plus 1. Here we have 3, and then we have 1, and then we have 3, then we have 2, and then we have 2, right? So this is what? 2, 5, 6, 9, 2, 5, 6, 9, 11, 13, 12. Oh, here. Yeah, this one. This should be 2. This one is 2. That's why the total is 12, right? Okay, cool. And so if you guys remember the maze 1, the original maze problem, for the original maze problem, it just asks you if this ball can reach this this destination or not. It doesn't ask you the smallest distance to reach it, right? And yeah, oh, okay. So here's another example here. So for this one, the answer will be -1 because here's the destination, but since the ball can only stop while it hits the wall, as you guys can see, so the ball will never stop at here because no matter if the ball is rolling in this direction or in this direction, it can only pass this destination, but it will never stop at it. That's why the answer is it's -1. Okay. And cool. So since this one I ask us to find the shortest distance, we cannot use the basic the DFS or BFS to explore all the possible routes, right? And then we also maintain like a visited nodes because that may not lead us the optimal solution, right? And why is that? Because let's say the ball move here and then here, right? So when the ball is here, it has like 2 options. It can either go right or go left. Yeah, because this one has already been visited. That's why the ball will only go right and left. But the optimal solution is go left because if you go right, and then you go to left, the total distance will be bigger. Okay, that's why we need to use another like algorithm Okay, and so if you guys know there's a this Dijkstra algorithm, basically the Dijkstra algorithm can help us to calculate the minimum distance in a graph, right? In a weighted graph, between any two nodes, right? So it's a perfect fit for this problem because for this problem, from here, from the starting point to the ending point, that's the two nodes in the graph, and from the starting point we can have different like edges, right? So and we can also have like different nodes. So the nodes will be the other stopping point. For example, this is also like a node. This is also a node. Here is also a node, right? And between those kind of nodes, there's like kind of like the weight on this edge, right? So the weight would simply be the distance in this case, and we're getting the minimum like total distance between these two nodes, right? So if we can model this problem into a Dijkstra problem, then the rest should be pretty straightforward, right? Where we just need to use the Dijkstra problem template, which is uh, the while loop, right? A BFS or DFS plus the priority queue. Okay. And yeah, then let's start coding. So for those who don't know the Dijkstra problem, I think you can just search online. There are like a bunch of other like videos or articles that can give you the very detailed explanation about why the Dijkstra problem works. So long story short, right? We define like m times n distance. So where the m is the maze and the n is the of the maze 0. So we define like two-dimensional distance here. At the beginning, everything will be the max size, okay? And then for n, this. So this two-dimensional list stores the minimum distance between the two nodes. Okay, and we also gonna be maintaining like the priority queue. So the priority queue, the key for the priority queue will be. So the key for the priority queue will be the basically the distance to this current location, right? Which will be the starting from 0 and start 1. So the key will be the distance, right? The current distance, and then the coordinates I and j. And if there are like multiple paths that can reach to this I and j, we could have different like distance, right? And then that's why we use the priority queue, because if we create and maintain the key in this way, the first one, right? So the first one will always be the smallest distance to the current direction, to the current location, because if this one is I and j, right? So this one is I and j. If we have a multiple route can lead to this one, right? Now we always obviously want to use that, the total cost. So this ij means that from the starting point, right? This is the starting point. From the starting point to the I and the j node, right? Where's the some coordinates in this graph, right? And then what is the distance, right? from the starting point to this current one, right? If there are like multiple paths that can lead to this I and j here, for example, if this one, right? Basically, we may have multiple entry points or items in this priority queue for the same I and j, and every time we'll pick the smallest one because we want to get the shortest distance, right? That's why we use the priority queue to get the shortest. We always process the smallest distance from the priority queue, so that we can make sure we'll always find the smallest distance from the starting point to any ij location. And after that, we're also going to be updating the distance because we'll be using this distance two-dimensional list here to maintain what is the current minimum distance from the starting point to this I and j position. And then every time when we find a smaller or like a shorter distance path, we update that. And that's the basic idea of the Dijkstra problem or Dijkstra algorithm. And okay, so here we need a base case, right? So the base case is the start and destination. It's going to be a start of 0 and start of 1. It's going to be 0, right? So obviously, the starting point and itself has a distance of 0. And then for the priority queue, we have 0 at the beginning, and then we're also going to be maintaining like a visited set, right? And then 4 directions, right? So this is a standard thing. 1 0 0 1 -1 0 0 -1, right? So while the product queue is not empty, right? So we have a current distance, right? And then we have I and j. We pop it from the product queue. Heap pop product queue. And then we only insert into the visited set whenever we pop it out from the priority queue. Okay, so this is important because that's the time we can be sure we have picked the correct distance for this I and j. Add I and j. Okay, and then we're gonna try different edges, right? So and the edges here or the neighbors for the current node will be rolling into 4 directions, right? So we have 4D in directions, and then a new I gonna be I, and new J will be J, right? And a new distance, okay, we'll be starting from 0, and then basically we'll try to roll in 4 directions, right? So basically, while this one is new I plus D0, and the new J is also in the range of n, right? D1 for this one, right? And the maze new I plus D0 and the new J plus D1 is equal to 0, right? So we keep rolling until we hit the wall, right? And then we increase the new I and new J. And then we also increase the distance, okay? So after the while loop, the ball has stopped, right? Stopped rolling. And then we need to check the if the new I and new J first, if it has not been visited before, right? And the distance, right? And the current distance plus the new distance is smaller than the distance of new I and new J, right? This this part is all like what part of the Dijkstra problem, Dijkstra algorithm, right? And then we push it into the product queue, right? With the new smaller distance for the current for this new I and new j, and then don't forget to update this one, the destination. Gonna be new I, new j equals to this. Oops, this one. Okay. Yeah, so that's it. So basically, after the while loop here, we will have a distance that can tell us, the shortest distance from the starting position to all of the other nodes in this graph. And then we can simply return, right, the distance of the destination 0 and destination 1. Right. Oh, this one's too long. Okay. 0 and destination 1, right? But, don't forget, we also need to handle this -1 case. So what would be the -1 scenario? Okay, obviously, if we will never be able to reach the destination, so the value for this destination in the distance array or two-dimensional 2D array will be remain to the system max size, right? As long as there's a way we can reach that. This one will definitely be updated with a much smaller value, right? That's why we only return this one if this one is smaller than system dot max size. Otherwise -1. Okay. Heap push. That's it. Yep. So there you go. Right, it works. So the time complexity for Dijkstra, I think it's it's m times n times log m times n. Yeah, I think this is the one. This is the one because the worst case scenario will be inserting everything into the priority queue, right? That's why the worst case scenario for the priority queue is this one, and we'll be inserting for each of the node will be using this priority queue, right? So I think that's it. This one, it's pretty interesting problem. As long as you can realize that, this one, every time when you guys say this kind of shortest distance, always try, and you can see it's a could be like a graph related problem, and then you're asked to get the shortest distance, and then definitely try the Dijkstra algorithm. It's pretty useful, and it's not that difficult to remember and to implement, right? Cool. I think I'll just stop here, and thank you for watching this video, guys, and stay tuned. See you guys soon. Bye bye.